In this screencast, we are going to work through deriving the differential equations for mass transfer in Cartesian coordinates. For those familiar with this approach in momentum and heat transfer, we will be using a shell balance method to derive these equations. This should help you see where they come from and therefore allow you to use this approach given other conditions. So let's start with a control volume. And we're going to say it has sides dx, dy, and dz. So some differential length in those three coordinates. So through this control volume, we have some mixture that contains A and let's say some other species. And it flows through this control volume. So if we go back and think about the Reynolds transport theorem, we could write out the following integral form of the conservation of mass through this control volume. Our first term evaluates the net flux of mass in and out of our control volume through the control surfaces, hence why I have CS. So we evaluate the dot product of our velocity times our density over our differential areas for each of the control surfaces that mass transfers through. Then we also add the following term for the control volume, which is our net rate of accumulation of mass within the control volume with time. Now we say that this has to be equal to 0. However, since A could be involved in a reaction, whether it's consumed or produced, we also need a term to account for this reaction. So what we're going to do is subtract out the net rate of production of A on the left side so everything is still equal to 0. I'll show you what that looks like. So this is our overall conservation of mass. So what we're going to do is expand these terms and write it based on our control volume dimensions that we have above. So let's start by looking at the mass flux in and out of the X direction. We know that a mass flow rate is just equal to the density of the fluid times the volumetric flow. And we could rewrite this as the density of the fluid times the velocity of our species, in this case we're working with A, times the area at which A is passing through. So we look in the X direction, we could redefine this mass flow rate as a mass flux. So I'm going to rewrite it as MAX to indicate that we are looking in the X direction for the mass flux of A. And so really what I'm doing is dividing by this area on this side so that we're setting this mass flux equal to rho VA. So now you see that we have that up in our term, and for our X direction I could write our mass flux in the X direction times our differential area. In this case it's dy dz. So for it entering, we would evaluate this at X, and then we would do the same thing on the other side of our control volume. So if I put X here and X plus some change in X, differential change in X, delta X, on the other side, then we'd also be evaluating this through the same cross-sectional area at X plus delta X. Now the problem with the way we wrote this is that if we have more mass coming into our control volume than leaving, then this value that we've written is going to be positive. And if you look back at our equation up here, a positive value for our net flux means that our accumulation term has to be negative, but that's not the case here. Assuming that there is no reaction, we would have to have a positive accumulation because that's what's actually occurring. More is going into the control volume than that's leaving. So we actually need to write this balance, this net flux, in the opposite manner. So now we have our mass flux in the X direction times its cross-sectional area to give us a mass flow rate. And we're evaluating this on the exit side minus what's coming in to give us our net flux term. So we can do the same for our Y and our Z. So now we've written our net mass flux terms that are coming in and out of our control volume. So now let's work on our second term, the rate of accumulation. So if we look at this term here, we could just rewrite this as d rho of A dt times our differential volume, in this case delta X, delta Y, delta Z. The rate of generation of A is written in a very similar manner. Since we had that on a per volume basis, we are just multiplying this by our differential volume, delta X, delta Y, delta Z, and then the dimensions will just be mass over time, which are the dimensions for the other two terms. Now we put all these terms together and set them equal to 0 like we had before. We're going to divide everything by this volume term, delta X, delta Y, delta Z, and evaluate in the limit as delta x, delta y, delta z approach 0 for our differential volume. And what happens? We get the following simplification. We could write these three terms together, as you've seen before, as the gradient operator of our mass flux of A. We're going to bring over our accumulation term and subtract out our reaction term, set this all equal to 0. Now we have our differential equation for mass transfer of A. So you can see the dimensions on each of these terms are mass per volume per time. Our mass flux is being evaluated in each direction, so we get a mass per volume per time. So we can do the same thing on a molar basis, so I want to do that really quick. So if we look at the moles of A entering our control volume, the moles of A leaving our control volume, we'll have some change in moles with time inside of our control volume, plus whatever moles we generate or take away based on a reaction. Now another way to write this is if we do this on a per volume basis, just like we did with the mass differential equation above. So now this becomes moles per volume, or concentration of A. We could rewrite our moles generated as a reaction term. So I'm going to write a large RA. So this becomes a molar production of A per volume, whereas before we wrote it as little RA to indicate it was a mass per volume per time. And one way we could rewrite our moles of A in is to write it as the flux of A, like we did above for the flux of mass. So the flux of A, molar flux of A, we write as NA. Again, maybe in this case I'm writing it in as X, and that's going to be times our area. So that's the same thing as moles of molar flow rate in, and so our molar flow rate out will be the flux of X times A on the other side. But as we said, we were doing this whole thing on a per volume basis. So let me write out what this looks like. We have our flux of A in minus our flux of A out. And recall that we had to rewrite this the other way to make it balance properly. Now if we multiply this by our area and we divide by our volume, then we get the following term. We then can add our accumulation term and subtract out the rate of production of A. We set this all equal to 0, and it almost looks good, except this doesn't quite look the same as it did for the mass equation. However, hopefully you see the similarities. The dimensions will give us a length on the bottom, so when we take the flux and we're evaluating it on each control surface, then indeed what we get is that this becomes the gradient of our molar flux of A. So hopefully you can see how we started with our integral equations, looked at a control volume, did a shell balance, and came up with our differential equations of mass transfer.